Hello, my name is Bradley Ryan, and I'm a graduate student at Iowa State University. And today I'll be talking to you about how we can use a combination of experimental and computational techniques to probe a somewhat unconventional material system. Specifically, I'll be talking about my research on silicon nanosheets that have direct bandgap-like behavior. So, semiconductors play a critical role in modern society. And it goes without saying that the workhorse behind all of these electronic devices is silicon. But if you look at the way we've been moving over the past couple of decades, we've been moving away from electronic devices and have been moving towards more modern optoelectronic devices. But this poses a threat for silicon. Silicon is a poor emitter of light, and this makes it nearly useless for many optoelectronic applications. There are those that are trying to mitigate this problem by developing new materials, but oftentimes these new materials fall short where silicon shines most. Silicon is earth abundant, it is non-toxic, and we have billions of dollars of infrastructure dedicated towards manufacturing, purifying, and distributing silicon. So, one key objective of my research is to fundamentally improve the ability for silicon to emit light. And with 2D materials such as graphene and 2D lead halide perovskites on the forefront of research, an obvious direction to explore is two-dimensional silicon nanosheets. And the most natural place to start is in the beginning. In 1863, Friedrich Wöhler published a paper titled About Compounds of Silicon with Oxygen and Hydrogen. And in this paper, he was the first to describe the reaction between calcium disilicide and hydrochloric acid. Calcium disilicide is an interesting compound by itself. It is comprised of silicon monolayers that are intercalated with calcium ions. And in this schematic here, calcium is in orange and the silicon is in blue. If we look at these silicon monolayers, they're comprised of a hexagonal arrangement of silicon atoms, and this would be analogous to monolayers of silicon 111 planes. And interestingly, if we combine calcium disilicide and hydrochloric acid, the product of this reaction, despite over 156 years, it is largely ill-defined. But perhaps the most profound property of this product is that it's comprised of silicon and it can emit light in the form of photoluminescence. And if you look at the literature, it makes itself abundantly clear that the product of this reaction, its structure, is unknown. So what I'm showing are just a number of different structural models that have been proposed over the years, some of them quite recent, some of them a bit older. So because of this discrepancy, the main goal of the research that I'm presenting here today is to determine the structure of the nanosheets that are derived from the reaction between calcium disilicide and hydrochloric acid. So what I'm showing here is just a schematic of the reaction. We take this black calcium disilicide powder and we combine it with aqueous hydrochloric acid and follow that up with a methanol wash to remove the calcium chloride. And what we're left with is this fluffy yellow powder. And this volume expansion that we're seeing is representative of the reaction. So you can see that the nanosheets expand quite a bit compared to the calcium disilicide. Here on the bottom left, this is the calcium disilicide precursor. On the right, this is the silicon nanosheet product. And interestingly, this product here diffracts X-rays rather poorly. So this can shed some light on why the structure of this product is so ill-defined, because the tools that we typically use to characterize the structure of this material don't work. So if we look at TEM, we can see that the product is clearly comprised of very thin nanosheets. Now I'm just showing two different perspectives here. One of them is top-down, where we can see through the nanosheets. And on the bottom here, this is looking at the sheets on the edge, as if you were looking down the pages of a closed book. And an SEM-EDS analysis clearly indicates that these nanosheets are comprised of silicon. So this is the central hypothesis that we were testing throughout all of this research. We hypothesized that when we combine calcium disilicide with hydrochloric acid, the product of this reaction would consist of a hexagonal arrangement of silicon atoms and each silicon atom is terminated with a proton. And this would be the overall reaction here. So then we turn to vibrational spectroscopy, and specifically we were looking at Raman and FTIR. The experimental data is shown here in black in both of these, and because this material system was relatively straightforward and easy to model computationally, we turned towards density functional theory calculations, and we wanted to look at the vibrational spectra as predicted by density functional theory. So we started out with a purely hydrogen-terminated silicon monolayer, and we compared the experimental and computationally predicted vibrational spectrum. And when we looked at Raman, we were pleasantly surprised that nearly all of the features that were predicted from a purely hydrogen-terminated silicon nanosheet were consistent with what we found with the experimental data. But when we looked at FTIR, it became clear that there were a couple of features that we were missing within our structural model. So we looked at the literature, and we looked at different vibrational modes in silicon-containing compounds, and we came up with a couple of new structures, specifically those that contained SiOH, SiH2, and SiCl bonds. And with these different structures, we could simulate these different vibrational spectra. And what we did is we took a linear combination of the predicted vibrational spectra to generate the computational vibrational spectra that you see here in red. And it's important to note that we used the same linear combination for both Raman and FTIR. So this provides a little bit of validation to the linear combination that we used. And an interesting thing that we found was that the intensity of these peaks is not proportional to concentration. I know it can be easy to think that because something has a more intense feature, it is in higher concentration, but our DFT results demonstrate otherwise. Specifically, we found that the SiOSI features were about 30 times greater in intensity than the SiH features for the same concentration. And because we were modeling these vibrational modes with density functional theory, we could actually visually inspect the vibrational modes. And of course, this is not something we can do experimentally. So this is one of the big advantages of computational techniques. So what I'm showing here are a couple of Raman active modes. We can see we have silicon-silicon bonds, a couple of different silicon-hydrogen bonds, and an SiOH mode. Similarly, we can do this with FTIR. And again, I'm just showing a handful. So silicon-hydrogen bonds, SiOH, and a silicon-chlorine vibration as well. And this was great. It provided us with a good idea of what atoms were bonded to each other in the system, but what we were ultimately after was the structure. And with X-ray diffraction out of our reach, we wanted to turn towards something else. And we looked at solid-state NMR spectroscopy. And this was done with a collaborator here at Iowa State, Aaron Rossini. He does fantastic NMR, so I would like to thank him for his help with this. So here on the top left, this is a proton NMR spectrum, and we can see that it consists of 3 different contributions. 2 of them being an Si3 SiH mode, and that's consistent with this type of structural model here. So if we take a given silicon atom, we can see that it has a proton terminated on the surface, and that silicon hydride is bonded to 3 other silicon atoms. So that's what these Si3 SiH features come from. We also have an Si3 SiOH mode that occurs, and you can see it's quite a bit less in intensity. Then we turn to a 29 silicon NMR spectrum. And there were 2 different experiments that were run. One of them probed protons that were spatially proximate to a silicon center, and the other showed protons that were chemically bonded to a silicon center. And what we can see is that, in general, the peaks line up quite well, meaning that the protons that are spatially proximate to a silicon are also chemically bonded. But we do see an SiX feature that is currently under investigation. We think it's silicon chlorine, but we still need to demonstrate that. Here on the top right, this is a 2D NMR spectrum. And things that occur along this main diagonal are chemically bonded to itself. So the fact that this Si3-SiH feature exists along this main diagonal means that we have this type of silicon hydride that's bonded to 3 other silicon atoms, chemically bonded to itself. So if you think about it, the only way that that can happen is if we have this type of hexagonal arrangement of silicon atoms, where each silicon atom is terminated with a proton. And we also see that this SiX feature here shows up off the main diagonal, and that it is chemically bonded to an Si3-SiH. So this means that these SiX features do not exist as islands of SiX, but instead they're just lone SiX groups in the middle of a bunch of Si3-SiH groups. Lastly, we looked at the J-coupling evolution. And this type of experiment here is sensitive to the multiplicity of different atoms. And what we're showing is 2 different types of evolution time, proton and silicon evolution time. And we can see that the frequency of these different evolution times are consistent between the 2 different types of evolutions. And this frequency of about 120 Hertz is consistent with a silicon monohydride. So this means that every proton is bound to a single silicon, and that is expected. But importantly, for every silicon, it is bound to a single proton. So again, this is consistent with this type of structure here. And we think that we don't see many SiH2 modes because the sheets, the concentration of the SiH2 modes on the edges of the sheet are just in much less concentration relative to the monohydrides that are along the surface. Lastly, we looked at the optoelectronic properties. So here, what I'm showing is absorbance here on the top left. And again, experimental data is in black, and the computational data is here in red. And it's generally well known that density functional theory tends to overestimate band gaps when we're looking at dielectric function. And that is how this red curve here was derived from the dielectric function. We can see that we observe an onset of absorbance at about 500 nanometers. And if we look at this main feature here, we find that that peak arises from the transition from the gamma point, the top of the valence band, to actually the second transition along the gamma point in the conduction band. If we look at the photoluminescence, we can see that it is comprised of 2 different contributions, one of them centered at 500 nanometers, right at the onset of absorption, and this is consistent with a direct bandgap-like material. And the other is at a lower energy of about 545 nanometers. Now, the exact nature of where these 2 different contributions come from is a little bit difficult to probe, but one possible explanation is found here if we look at the band structure. So the band structure, if we look at the conduction band, we can see that there's a direct transition here at about 2.26 eV, and then the indirect transition is about 0.1 electron volts lower in energy than this direct transition. So it's an almost direct band gap, but technically speaking, it is indirect. Now, because quantum confinement effects are certainly at play here, it's not unreasonable, due to the Heisenberg uncertainty principle, that there is a superposition of momentum states here. So it is possible that we could have emission from this indirect transition that is contributing to this lower energy feature here. But experiments have demonstrated that it's actually pretty difficult to probe that type of emission. If we look at the time resolved photoluminescence, we find that it has an average lifetime of about 16 nanoseconds and a photoluminescence quantum yield of about 10%. For the sake of time, I think I will omit the conversation here about the frontier orbitals, but if you're interested in a discussion on those, I would refer you to the paper here. So, in conclusion, our results indicate that the product of the reaction between calcium disilicide and hydrochloric acid is the silicon analog of graphene, that is hydrogenated graphene, and this would be called silicane. We find that the silicon atoms, just like in graphene, are hexagonally arranged and comprise of a monolayer terminated with protons. We also find that the silicon nanosheets have a nearly direct band gap. So, I would very much like to thank our collaborators, Aaron Rossini for the solid-state NMR, Emily Smith for the Raman spectroscopy, and Jigong Wang for the time-resolved photoluminescence. So with that, if there are any questions, I'd be happy to take them.